It says around.
Yeah, no.
There's 72. But that was like the average.
You get like everything wrong from like.
I didn't see my show doesn't work, so I can't see. I gotta go into the juice bar.
I'm pretty sure the teacher misgraded mine because I definitely got a question wrong in the GPA. Good look at this guy. He's like, I got a 70 graded wrong.
Oh, we're just like, I'm pretty sure I got it created.
I got a 90.
Well,
It was the first page was really hard.
if I can do the corrections and get the AP wrong, I can get like
It's
so
the
it's like
first.
not a bad grade. at all.
Yeah, 73 is close.
Yeah.
Going to DC.
How many points did you get?
Well, you get a third up to 1 and 5 back for correction.
Right.
No, it's only up to 100.
But yeah,
But it's out of the 1 and 5. So 22, no, 32. Wait,
But 3 is 10 points.
yeah, 32, so round up, it'll be 11.
No.
yeah, it's 84.
84. And then 12 for, if I get all the AP, which I probably will, then I get 96.
Really doing that.
Well, I can get an A.
Really doing that.
Friday average.
It's because I forgot all the solubility rules. Aren't they doing like New Year's solubility?
That, plus I don't remember using solubility.
It was like they give you a bunch of
that's
solubility.
Yeah.
I never did that.
Wait, we need to know what
They
solubility.
gave you a
I
bunch of
just
salt.
like didn't get the kind of all in that solubility unit. The first.
Oh, yeah, they just.
Every solubility.
Yeah.
I didn't know mine, but I just, like,
Also, like if you remember them, look back.
Yeah, my show be just like, it just says like.
Yeah, mine does that too.
Did you do something about it? What did you do?
No, I just took shots on paper.
Oh,
I'm trying to keep you updated.
I gotta go.
No, I think this year, not updated.
Next period.
I'm trying to update your show me.
man.
I go to the juice bar.
Well, have you tried turning off your iPad?
You know, it's coming back like.
Isn't that always the solution? All right, guys, we have a fairly short notes today, and then you guys do have a problem set due today over the first 2 sets of notes. So if you haven't finished that, make sure that gets done and turned in. My intention was to have no homework over spring break, so don't really want you like working into the evening on that. It just finish it, get it turned in, be done. And then have a spring break, hopefully where you don't have to think about school and you don't have to stare at a computer screen and you don't have to do all that stuff. Today we are going over a diagonalization that is on the next problem set, which is due a week after we get back. So I wouldn't really stress about working on that over your break. Again, I just want you guys to take a break. So we're going to do diagonalization, fairly short lesson. Oops, that's yes, last periods. So with diagonalizing a matrix, this is kind of similar to factoring. We're factoring it into different factors here, but it ties in with what we were doing yesterday in terms of like multiplying a matrix by itself over and over and over. This is another related way to do it using eigenvectors and eigenvalues. I prefer this one, but it's really the same thing. Like you can kind of choose which one you like better, whether it's take your vector, find it, what linear combination of the eigenvectors it is, and then add those together after multiplying by the eigenvalues to whatever power. This way to me is a little bit more streamlined. So I kind of like the diagonalizing better, but again, they do the same thing. So with diagonalizing a matrix, we're essentially going to factor it to a set of matrices where one of them is a diagonal matrix. Okay, a diagonal matrix being a matrix where you just have any non-zeros are on the main diagonal, everything else is 0. Diagonal matrices are really good to work with because they have They're easy to multiply, they're easy to invert. If you take a diagonal matrix, the inverse is just all those entries take the reciprocal. So it'd be 1 and 1/2 and 1/3 would be your inverse. If I multiply two together, normally I do a bunch of dot products of rows and columns, but most of the products here will be 0 because of the way this is set up. So really, the only ones you have to multiply are row 1 and column 1. So really, element 1, 1 from both. Row 2 and column 2. So really, the element on the second row with the element on the second row, 8. And then the third and the third, so 18. So like diagonal matrices are really easy to multiply because you're not doing a bunch of dot products and adding a bunch of things together. You're just multiplying these two numbers, and then these two numbers, and then these two numbers. So we like diagonals, and again, that'll be the main thing that we'll find useful in the application. It'll be that idea that we can multiply these things very easily together. Okay, so say we had this n by n matrix. We need n linearly independent eigenvectors in order to diagonalize a matrix, because we're going to need an inverse for the eigenvector matrix. So we'll put a bunch of eigenvectors into a matrix. We call that S. It needs an inverse, which means they need to be independent. So we'll need to have found independent ones. So some of you guys are already asking questions on the problem set and saying, I got eigenvector 0, 0, 0. That can't be an eigenvector. Eigenvectors should be non-zero. They should be independent vectors. So don't give me, yes, I understand that like 1, 1, 1, 1 times 0 equals 0. That doesn't mean 0 is an eigenvector. It means -1, 1 is your eigenvector, because that's what I'd add. Okay, so don't give me 0 as your eigenvector, because yes, I get that that will make 0, but that's not the one we're looking for. We're looking for the other ones. So I want those non-zero, those independent ones. Then what we'll see is that S inverse AS is going to give me this thing called lambda. That's a capital lambda. That is a diagonal matrix with the eigenvalues on the diagonal. So think when we do A times S, since S is the eigenvectors, what we're going to get for each column is A times the first column is A times an eigenvector. Will give me a multiple of that eigenvector. The second column, I'll get a multiple of that one. The third column, I'll get a multiple of that. And then when I multiply by the inverse, it's basically going to leave behind the multiples that I'm getting there, times the identity, because it's going to be S inverse times S will be the identity. But since I multiplied by A, I'm not going to get the identity. I'm going to get the identity with those multiples on the main diagonal. We typically don't use this form. This is how you kind of come up with the why it works this way. But usually we're not interested in what lambda equals. We're interested in what A equals. So we take that S inverse AS equals lambda. We'll multiply from the left by S, and we'll get rid of this. Multiply from the right by S inverse, and that'll get rid of that. And so we typically use A equals S lambda S inverse. Where again, S is just a matrix made of the eigenvectors as columns. Lambda is the diagonal matrix with the eigenvalues on the diagonal. And then S inverse is the inverse of S, okay, which we will have to find there. So like before, we'll do a lot of 2 by 2s, so finding the inverse shouldn't be hard. Any of the ones that are like 3 by 3s or bigger will probably have a lot of zeros, make it as easy as possible to invert that S matrix. Again, since we need an inverse, we have to have independent eigenvectors, which means you won't always be able to diagonalize. If I can't get independent eigenvectors, I can't diagonalize the matrix. Repeated eigenvalues are okay. as long as you can get independent eigenvectors. So for example, if we had 2, 5, 0, 2, I picked some easy ones that don't want to spend a bunch of time refinding eigenvalues. So this one will give us eigenvalues 2 and 2. Right, it's a triangular matrix, which means it's just the diagonal entries. If we subtract, we get 0, 5, 0, 0, and we're going to find the null space of that one. Oops. So something times 0 plus something times 5 gives me 0. And then something times 0 plus something times 0 gives me 0. The second row doesn't really help, but the first row, think that first number can be anything. Right? I could take 1 times 0, but then that second number is going to have to be 0 because there's no multiple of 0 that I can add to a multiple of 5 unless that multiple of 5 is 0 times 5. It's going to give me 0, right? If I take 0 plus something times 5 equals 0, that second thing's going to have to be 0. Which really means there is no independent one I can get for the other two, right? This one would give me the exact same matrix. And I'm not going to be able to solve for something else. X2 is going to have to be a multiple of 1, 0 as well. So this matrix is not diagonalizable because I would not be able to come up with an independent eigenvector, which means S won't have independent columns, which means S won't have an inverse. Okay, so this would be an example where, yeah, you won't get independent ones here, but just because I get the same eigenvalues, it doesn't mean that will always happen. So like here, I have the same eigenvalues, 2 and 2. This time when I subtract and I go to find the null space, I do have multiple options here, not just one, right? X1 could be basically anything. 1, 1, right? That'll be 0, give me 0. 1, 0, 0, 1, negative 1, 1, 1, negative 1, 2, 10, whatever you want it to be, which means here I could find another independent one. X2 could be 1, 0, which is independent, or 0, 1, or negative 1, 1, or 1, negative 1. You could pick some other independent one. So just because you have the same eigenvalues does not mean you can't have the same eigenvectors. I mean, can't have different eigenvectors. The key here is look at what we've done. We're finding a null space of this thing here. So as long as I've got 2 free variables, which I do here, I have no pivots, which means I have 2 free variables, I can come up with 2 independent null space solutions. Here, I have 1 pivot and no 1 free variable, which means I can only have 1 independent solution. So think of what we've been doing. When I go to this step to find the null space, if I have 1 free variable, there's only 1 independent vector I'm going to be able to find in the null space. If I've got 2, there's 2. If I've got 5, there's 5. So if I had a bunch of rows, I could technically maybe come up with 5 different ones as long as I had 5 free variables. I can come up with independent ones, 1 for every free variable. Not free variables of this. Okay, after subtracting the eigenvalue, that's where I can come up with this. Okay, so again, if I already have different eigenvalues, you will definitely have independent eigenvectors. So if my eigenvalues are 1, 2, and 3, I will get different eigenvectors for sure. If my eigenvalues are the same, I may or may not be able to get independent eigenvectors. So again, think what you're getting with the free variables when I subtract. So I picked a bigger one here to have another example. But I still kept it diagonal so that we don't have to do a bunch of work finding eigenvalues. We're going to have eigenvalues 1, 0, and 0. So if I subtract the 1, I'll have 0, 2, 3, 0, negative 1, 0, 0, 0, negative 1 times x1 equals 0. Okay, my free variable is the first column. So we can let that be whatever we want. And then notice if that was 0, The other two would come out to be 0. I mean, sorry, if that was 1, the other two would come out to be 0, right? 1, 0, 0 times 0, 2, 3, or 0, negative 1, 0, or 0, 0, negative 1. Those will all come out to be 0. So I can basically make that first number whatever I want. If I subtract 0, now notice I've got 2 free variables, which means I will be able to come up with 2 independent vectors that make this thing 0. So just think again what we did, I don't even know, lesson 5 or 6 or something. My free variables are the second and third. So like let the second one be 1, let the third one be 0. And then look what the first one would have to be, -2. Right? -2 times 1 plus 2 times 1 plus 0 times 3 is 0. Obviously, the second and third rows will be 0 as well. To get my third one, I would use the exact same equations because I've got the exact same eigenvalue. This time, let the third one be 1 and the second one be 0. And notice that would mean the first has to be a -3. So that -3 times 1 plus 0 times 2 plus 1 times 3 gives me 0. And again, row 2 and row 3 is automatically going to give me 0. So repeated eigenvalues can give me independent eigenvectors. What I'm looking for is 2 free variables. I can get 2, which is what I need here. So like this matrix is diagonalizable. Okay, and it's really a diagonal matrix anyway, so it doesn't matter, but it is diagonalizable. Other ones can be too. It doesn't have to be something this simple. I just picked simple ones to kind of illustrate it. Okay, so we can take a matrix, and as long as we can come up with independent eigenvectors, we can diagonalize the matrix. So here we're going to diagonalize the matrix. So we have 5 minus lambda, -3, 1, 1 minus lambda. We multiply and we get, 5. Minus 6 lambda plus lambda squared plus 3 minus a -3 equals 0. So that's lambda squared minus 6 lambda plus 8, which is lambda minus 2 times lambda minus 4. So we have 2 eigenvalues, 2 and 4. Okay, for 2, we're going to find the null space of 3, -3, 1, -1. Which is 1, 1. Right, 3 plus -3 and 1 plus -1 will give me 0. For 4, we'll find the null space of 1, -3, 1, -3. Oops, say 3 and I read a 4. So this time I would choose 3, 1. And then for A, our first matrix is just the columns are the eigenvectors. So my columns would be 1, 1, 3, 1. My next one is just the eigenvalues on the diagonal of a diagonal matrix. So 2, 0, 0, 4. My third one, again, if it was a large matrix, this would be the one that's the most work. I need the determinant of S, which is this one here, because I'm going to have to find the inverse. So the determinant is 1 minus 3, which is -2. And so then I want the inverse as my third matrix of that first one. So all I do is I switch the numbers on the main diagonal and divide by the determinant. So I'll switch the 1s and then divide by the determinant. And so I'll have a -1/2, -1/2. And then I'll switch the signs on the other diagonal and divide by the determinant. So I'll have a -3 over -2, which is 3/2, and a -1 over -2, which is a +1/2. And so with a 2 by 2, we can do it fairly easily. With a 3 by 3 or 4 by 4 or 5 by 5, that's probably going to be your one of your harder steps, is inverting that matrix. But again, we'll mostly do 2 by 2s or maybe really simple 3s or something like that. And so I multiply these 3 together, I should get 5, -3, 1, 1. I should get A back. Okay, our main benefit is similar to what we saw yesterday with our eigenvalues and eigenvectors. In diagonalized form, it's really easy to multiply A multiple times. So like A squared would be S lambda S inverse times S lambda S inverse. Right, that's A times A. We'll notice these middle S inverse times S will give me the identity. And this will be S times lambda squared S inverse. Remembering that lambda is a diagonal matrix, so lambda squared, all I'll have to do is square the diagonal. Okay, multiplying a diagonal by itself many, many times is really easy. You just square or cube or whatever the diagonal entries. You don't have to sit there and do matrix multiplication. Meaning if I just kept going, A cubed would be S lambda cubed S inverse. A to the 4th would be S lambda to the 4th S inverse. So we can get a formula for A to the K. I wouldn't have to do anything to my S. I would just raise all my diagonal entries to the K. And then again, I wouldn't have to do anything to my S inverse. So if I wanted to multiply A 100 times by itself 100 times, or something else by A 100 times, I could do 100 matrix multiplications, or I can just raise the diagonal entries to the 100th and do these 3 matrix multiplications, okay, which is far, 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 far fewer calculations. So picture you're doing large matrices and large amounts of multiplication. This reduces the computing power quite a bit. Okay, so we're going to come up with a formula for A to the K for this specific A. And then most of the homework and the tests and stuff, it's a similar idea. So I'm going to have 1 minus lambda. Oh, wait, I don't even have to do that, right? This is, you could do that, but this is a diagonal matrix. I mean, a triangular matrix, sorry. So my eigenvalues are 1 and 2. If you didn't see that, you could do it the longer way. But every time you see one of those shortcuts, go ahead and use it, because usually it's because we've already done that. And now we're trying to do something else, and I don't want you spending a bunch more time doing the same exact problems we already did in a different homework. So subtract 1, I'll have 0, 1, 0, 1 times x1 equals 0, which means x1 is 1, 0, right? 1 times 0 plus 0 times 1, and 1 times 0 plus 0 times 1 will give me 0. For 2, I'll have -1, 1, 0, 0 times x2 is 0. So my eigenvector would be 1, 1. Right? 1 times -1 plus 1 times 1 equals 0, and 1 times 0 plus 1 times 0 is also 0. Then A to the K, well, we'll factor A first, and then we'll do A to the K. So A is going to be 1, 0, and 1, 1. The diagonal matrix with 1 and 2 on the diagonal. And again, we'll need the determinant of S, which is this matrix here, is 1 minus 0, which is 1. I'll switch the numbers on the main diagonal, which are 1 and 1. So switch their places. They're still 1 and 1. Divide by 1, and they're still 1 and 1. So this one will have 1 and 1 here for the inverse. And then the other diagonal, switch the signs, divide by 1. I'll have a -1 and a 0. So there's my factored form. A to the K will then be 1, 1, 0, 1 times 1 to the K, 0, 0, 2 to the K times 1, -1, 0, 1. Okay, if we multiply that out, we'll have a model, a formula basically that'll give us one, we have one matrix that is a to the k, a to the second, a to the fifth, a to the 100th, whatever. So I multiply, first I'm going to multiply the first two matrices. I'll have 1 to the k plus 0, which is 1 to the k, which is really just 1. First row times the second column will give me 2 to the k. Second row times the first column will give me 0. Second row times second column will give me 2 to the k. And then multiply those two, and I have 1. I'll have a -1 plus a 2k, oh, 2 to the k, sorry. So 2 to the k minus 1. And then a 0, and then a 2 to the k. Okay, so like a squared, a times a is 1. 2 squared minus 1 is 3, 0, 2 squared is 4. A to the 5th is 1, 2 to the 5th is 32, minus 1 is 31, 0, 32. Okay, and you could basically get a to whatever power, as long as you can raise 2 to that power, you could get what a times itself 100 times is, or 1,000 times, or 1,000,000 times is, by taking 2 to the million, which may sound like a lot. It's really not, compared to multiplying matrix multiplication 1,000,000 times. That would be a lot. So this would be a formula for getting that, so that if we wanted like a to the k, oops, a to the k times some vector, I would just do, if I want a to the 5th, put that vector here, and that's a to the 5th times that vector, or whatever. All right, this also gives us an opportunity to use the commutative property. Normally, the commutative property is not true for matrix multiplication. But if they have the same eigenvectors, it will be true. So if I ever take two matrices and multiply them together, and it's the same forwards and backwards, that means they have the same eigenvectors. Okay, if they have the same eigenvectors, it means I could use the commutative property. This is really useful in proofs. Okay, that once I know they have the same eigenvectors, AB and BA are the same. Okay, so I'm going to kind of show why that's true. I'm not going to do like a full proof, but say they have the same eigenvector matrix S. Well, then A times B will be S, the lambdas of A times S inverse, and then S times the lambdas of B times S inverse. They have the same eigenvectors, not necessarily the same eigenvalues. Okay, same eigenvectors, which means these will cancel each other out because they will be the same. So this would be S lambda A lambda B times S inverse. If I switch the order and did B times A, I would just switch the order of those two things, and what I would get is S lambda B lambda A S inverse. But again, these are diagonal matrices, so those two products are the same, right? If I multiply two things with diagonal matrices, all I'm doing is multiplying the diagonals. So like if I have 2, 0, 0, 4 and 3, 0, 0, 5, all I'm going to do is do 2 times 3 and 4 times 5, whether it's in that order or switched. So those are the same. So AB will be equal to BA. Okay, if we start with AB equals BA, we can show that they also would have the same eigenvalues. I mean, eigenvectors, sorry. So say we have an eigenvector of A, that X is an eigenvector of A. Well, then if we take the AB equals BA and we just multiply both sides by X, the B times A times X should be the same as B times lambda times X, because A times X is lambda X. And so we have A times B times X equals lambda times b times x. Well, this means b times x is an eigenvector of A also, right? That's the definition, is that when I do A times bx, I get a multiple of bx. That means bx is also an eigenvector of A. So bx is a multiple of x itself, right? Since x was an eigenvector of A associated with lambda, and bx is an eigenvector of A associated with lambda, we're basically in a situation where every time I get one, I'm like, this is 1, 0, but you could use any multiple of that. We're basically saying bx has to be one of the other multiples, since that same lambda gives me that same eigenvector. Well, again, this is the definition of an eigenvector of B, right? Is that bx equals a multiple of x. So that's how you'd prove it, is we could start with an eigenvector of A and that AB equals BA, and show X would also be an eigenvector of B. Okay, but if we ever see the commutative property working for a certain set of matrices, that means they have the same eigenvectors. Or if you know they already have these same eigenvectors, you can use the commutative property with those two matrices. The eigenvalues don't matter. It's only the eigenvectors have to be the same. Okay, that's all we have today. So you guys have a good amount of time left if you still have to finish up problem set 8. Is that the last next one? I don't even know. 8, let's do today. You guys can work on that. You can work on something for another class, getting 8 turned in at some point. And you guys have a great week off. Hopefully you guys get to do something fun, and I'll see you guys in a week.
Thank you.
Thank you, Mr. Smith.